So I need to find out a gradient of this as well as gradient of this. What is j theta? J theta is your error function. So first thing first, you must have j theta which is differentiable. So I am not free, okay? I am not free to choose any cost function, but your cost function or error function must be differentiable. You should be able to find out the gradient, okay? So let's say a simple function that we always use. So half MSE, okay? So I have taken J as half MSE. There are two parameters, theta 0 and theta 1. And this could be written like this also. So 1 upon twice m, summation I is equal to 1 to m. M are number of sample points, okay? So y cap equation I can replace here. So it is theta 0 plus theta 1x. So this is replaced here. So this is y cap equation minus y bracket square. Now if I find out the gradient, let us differentiate this. So d j theta with respect to d theta 0. So what is the derivative? Last time we have seen this. So 1 upon twice m multiplied by 2. Okay. So this is like derivative of x square. So it is 2x into derivative of x term. So this is simply simple to understand. So 1 upon twice m into 2 theta 0 plus theta 1 xi minus y. So the term will remain as it is, but j theta with respect to d theta, so this is a constant term, okay? Uh, theta 0 with respect to j theta with respect to theta 0. So I'm very sorry. This is j theta, okay? J theta. So when I find out j theta with respect to d theta 0, okay? This is constant. This will be treated as constant. Okay, that's why the partial derivative will be 0 for this, and there is no term of x and y in the differentiation. Okay, got this? Whereas if I find the partial derivative of j theta with respect to d theta 1, I get the term of xi here, and this is very important to note. Okay, so when I find the gradients of any weight parameter, this is bias. Okay, so in bias, if I find the gradient doesn't depend upon the sample value, current sample value. Okay, so you don't get the term of xi here. Whereas for parameters w1, w2, w3 or theta 1, theta 2, theta 3, all these weight parameters always depend upon the current sample value. Okay, so this is very, very important to note the equation. Otherwise, both the equations are quite same. Okay, so let's me erase this first and going forward. Got this? So what is happening now? This 2 is getting cancelled. This is 2, this 2 and this 2 is getting cancelled. And this is the simple reason. That's why instead of taking the complete MSc, all the time we are taking half MSc. This is simple adjustment that we have done. Okay. So here is the comment that I have made. So factor of 2 in half MSc is getting cancelled in the gradient to make the gradient equation more simple. That is the reason we took this half MSc. Okay, nothing else. Okay, so what is important is your gradient equation must be differentiable. Okay, and note the partial derivative of j theta with respect to bias and j theta with respect to the parameter weight. So in weight equation you get the sample as it is, okay, whereas in bias you don't have the sample. Okay, and these are the update equations. So theta 0, new value of theta 0, you can find out old value minus alpha into the gradient. And what is the gradient? Here you have the gradient. So 1 by m summation I is equal to 1 to capital M. This is your y cap, okay, and this is minus y, okay. For all the samples, you have to find out this. Similarly, this is theta 1 and you get the term of xi here. So y cap minus y into xi. So hope you got this equations. Now in machine learning, we use very important activation functions. Later on we are going to see this in the neural network theory. Okay. Before we go into sigmoid and tanh, okay, let us understand what is threshold. Now all of you are electronic students and you know what is the activation, right? For example, if I have some, say, comparator like this, okay, and I have set some reference level here, some reference level, and this is the input. So what is the job of this comparator? It compares this input with the reference, and if it crosses this reference level, then only it gets activated and your output will be. Or same thing happens in the logical expressions also. Okay. In neuron, later on we are going to see neuron which we represent like this. You have the inputs coming from like this. Let's say X is the input. Okay. This is say bias. And then we are multiplying this X by say theta 1. This is bias, or you can say theta 0. What is the equation of the model? Here we write the equation as theta 1 into x plus b0. So we find out the sum. Now to get the y cap value, we set some threshold. We set some threshold. Okay. So we pass on this sum through some activation function. Okay. Like say sigmoid. And what is this sigmoid function? In general, it is written as 1 plus e raised to minus some variable z. So when I write sigmoid of z, it is this. Okay. So sigmoid of say my equation y cap. So what will be? So it will be 1 upon 1 plus e raised to minus into bracket theta 1 x plus theta 0. Got this? So this is a sigmoid function. We'll talk about this little later. So this sigmoid activation function, try to understand if I have to fire the neuron, if I have to turn on the neuron, if I have to activate the neuron, you should have some activation function defined in the neuron. Then only it will be fired. Otherwise, it will not register the output. It will not generate the output. So that kind of activation function should be there. And the important thing is activation functions must be differentiable. Okay. So very famous activation functions which we are going to look at is sigmoid or tanh. Okay. Now sigmoid already we have defined here. So see what happens if we differentiate the sigmoid function. Okay, let's see. So this is how we define the sigmoid function. Y cap is equal to 1 upon 1 plus e raised to minus z. And as I told you, I have to find out the sigmoid. That's why this is 1 upon 1 plus e raised to minus. This is my model, that is theta 1 x1 plus theta 0. Theta 1 xi into plus theta 0. So if I find out the derivative, this is the simple derivative. Just go through this. Okay. So I have to find out the gradient now. So let us define J first. Okay, so I have taken half MSE y cap minus y, and this y cap is replaced by sigmoid. Okay, so this 1 upon 1 plus e raised to minus this thing, that is replaced here. So now find out the derivative. So let us find out the gradient for updation for theta 0. So you have to differentiate this j function with respect to theta 0. Okay. So what do you get here? So you get